Hello students, I welcome you to my first lecture on equilibrium given as unit number 6 of chemistry for class 11 as per the NCERT syllabus. Chemical equilibria are important in numerous biological and environmental processes. For example, equilibria involving oxygen molecules and the protein hemoglobin play a crucial role in the transport as well as delivery of oxygen from our lungs to our muscles. Similar equilibria involving carbon monoxide molecules and hemoglobin account for the toxicity of carbon monoxide. When a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and the number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals the number of molecules returning to liquid from the vapor state. We say that the system has reached equilibrium state at this stage. However, this is not static equilibrium, and there is a lot of activity at the boundary between the liquid and the vapor as shown in the diagram. We say that the system has reached equilibrium state at this stage. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation. Equilibrium can be established for both physical processes and chemical reactions. Equilibrium mixture is the mixture of reactants and products in equilibrium state. That is, at equilibrium, the rate of evaporation is equal to the rate of condensation. For example, it can be represented as, in the case of H2O liquid getting converted on heating to H2O vapor and vice versa. The double half arrow as shown on the screen between H2O liquid and H2O vapor indicates that the processes in both the directions are going on simultaneously. Thus, the mixture of reactants and products in the equilibrium state is called the equilibrium mixture. The state of equilibrium can be observed in physical as well as chemical systems. The equilibrium can be static or dynamic. The reaction may be fast or slow depending on the experimental conditions and the nature of the reactants. When the reactants in a closed vessel at a particular temperature react to give products, the concentrations of reactants keep on decreasing, and while those of the products keep on increasing for some time, after which there is no change in the concentration of either the reactants or the products. At this stage, the system is dynamic equilibrium and the rates of forward and reverse reactions become equal. It is due to the dynamic equilibrium stage that there is no change in the concentrations of various species in the reaction mixture. The ionic equilibrium is the equilibrium involving ions in aqueous solution. As said earlier, equilibrium can be both in physical as well as chemical processes. Let us first discuss about the equilibrium in physical processes. The characteristics of a system at equilibrium are better understood if we examine some physical processes. The most familiar examples are that of the physical transformation processes. For example, solids on heating become liquid and on cooling become solid, or liquid on heating becomes gas, or on cooling gas becoming liquid. That is, some processes solid can become gas or gas can become solid. First, let us take solid to liquid equilibrium. Example is H2O in solid form on heating becomes, that is, H2O is ice in solid form is ice, on heating gets melted and becomes liquid, H2O liquid, and on liquid on cooling becomes H2O solid again. Below its freezing point, a liquid freezes spontaneously and liquid becomes solid, that is below the freezing point. When this is heated above its melting point, the solid melts spontaneously and solid becomes liquid. At the melting point, the two phases are in equilibrium, that is, solid becoming liquid and liquid becoming solid, because of the above two processes occur simultaneously at the same rate. Such an equilibrium is characterized by its temperature, that is, melting point of the solid. Liquid vapor equilibrium. Example is H2O, that is water in liquid form getting converted to vapor or steam. So H2O can become H2O vapor, and simultaneously it can also become vapor to liquid, that is liquid to vapor and vapor to liquid. The rate of evaporation is maximum in the beginning. As vapor builds up, the pressure increases and the rate of evaporation slows down. Also, the reverse process of condensation begins. At equilibrium, the vapor pressure reaches its maximum value and is known as saturated vapor pressure. So, at equilibrium, the vapor pressure reaches its maximum value and it is also called as saturated vapor pressure or simply the vapor pressure. At a fixed temperature, each liquid has its own characteristic vapor pressure. The vapor pressure of a liquid increases with increase in temperature. Next is the case of solid vapor equilibrium. For example, I2 in solid state gets converted into I2 vapor and vice versa, and in the reverse direction is also possible. That is, camphor solid becoming camphor vapor and camphor vapor getting converted to camphor solid. Volatile solids sublime to form vapor. This process of solid to vapor directly is called sublimation also. The situation is just similar to the liquid vapor system. When kept in a closed container at a constant temperature, the reaction can be written as solid to vapor and vapor to solid simultaneous formation. Equilibrium involving dissolution of solid or gases in liquids. First, let us take up the case of solids in liquids. We know from our experience that we can dissolve only a limited amount of sugar in a given amount of water at room temperature. If we make a thick sugar syrup solution by dissolving sugar at a higher temperature, then sugar crystals separate out if we cool the syrup to the room temperature. We call it a saturated solution when no more of solute can be dissolved in it at a given temperature. Thus, the solution gets saturated when no more of solute can be dissolved in at a given temperature. The concentration of solute in a saturated solution depends on the temperature. Please underline, the concentration depends on the temperature. In a saturated solution, a dynamic equilibrium exists between the solute molecules and in the solid state in the solution. Thus, the rate of dissolution of sugar equals rate of crystallization of sugar at equilibrium. The next case is that of gases in liquids. For example, carbon dioxide gas dissolving in a carbon dioxide solution. When a soda water bottle is opened, some of the carbon dioxide gas dissolved in it fizzes out rapidly. The phenomenon arises due to difference in solubility of carbon dioxide at a different pressure. So, in gases, pressure is very important. There is equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid under pressure. This equilibrium is governed by the Henry's law, which states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. So here underline the mass of a gas dissolved in a given mass of solvent, that is mass remaining constant of both solvent and solution at any given temperature is mass is proportional to pressure of the gas above the solvent. Now this is in the case of soda water bottle, the amount of gas dissolved decreases with increase in temperature. The soda water bottle is sealed under pressure of a gas when its solubility in water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition required for the lower pressure, namely its partial pressure in the atmosphere. This is how the soda water bottle, when left open to the air for some time, turns flat. Now we can generalize that for solid to liquid and liquid to solid equilibrium, there is only one temperature, that is melting point at 1 atmosphere, that is 1.013 bar, at which the two phases can coexist. If there is no exchange of heat with the surrounding, the mass of the two phases remains constant. For liquid to vapor and vapor to liquid equilibrium, the vapor pressure is constant at a given temperature. For dissolution of solids in liquids, the solubility is constant at a given temperature. Point number 4 is for dissolution of gases in liquids, the concentration of a gas in liquid is proportional to the pressure concentration of the gas over the liquid. Now we will just summarize the general characteristics of equilibria involving a physical process. The characteristics of a physical processes which are common to the system at equilibrium are: point number 1, equilibrium is possible only in a closed system at a given temperature. Please note that equilibrium is possible only in a closed system at a given temperature. There may be some multiple choice questions on this. Both the opposing processes occur at the same rate and there is a dynamic but stable condition. So here the rate is equal for opposing processes. All measurable properties of the system remain constant. When equilibrium is attained for a physical process, it is characterized by the constant value of one of its parameters at a given temperature. The magnitude of such quantities at any stage indicates the extent to which the physical process has proceeded before reaching the equilibrium. These points you may please note down. The table 1 shown on your screen summarizes some features of the physical equilibria. In the process of liquid to vapor and vapor to liquid, for example H2O, example is H2O liquid to H2O gas, that is vapor, H2O vapor, that is steam. The pressure of H2O is constant at a given temperature. The next example is solid to liquid. Example is H2O solid, that is ice, melts to become water, that is liquid. Here the ice melts, hence melting point is fixed at constant pressure. Then solid to solute solution, that is example is sugar syrup getting dissolved in the sugar solution. So the concentration of solute in solution is constant at a given temperature. Finally, gas in the gaseous state becoming gaseous liquid, that is soda water by example. For example, carbon dioxide gas dissolved in water, that is carbon dioxide aqueous. The gas aqueous, a gaseous pressure is constant at a given temperature. Then in the case of carbon dioxide aqueous to carbon dioxide gas is constant. Concentration, this is the symbol of concentration, is constant at a given temperature. Till now, we studied about the physical processes. In this section, we will study equilibrium in chemical processes. Analogous to physical systems, chemical reactions also attain state of equilibrium. These reactions can occur both in forward and backward directions. When the rates of the forward and reverse reactions become equal, the concentrations of reactants and products remain constant. This is the stage of chemical equilibrium. This equilibrium is dynamic in nature as it consists of forward reaction in which reactants give products, and in reverse reaction the products give the original reactants. Hence, if the process involves only chemical change, the equilibrium is called chemical equilibrium. Consider a dynamic reversible reaction shown in figure 1. Let A and B be the two reactants resulting in a forward reaction products C plus D, and in the reverse direction the product C plus D gives the original reactants A plus B. The figure on the screen shows the graph of attaining a chemical equilibrium. In the initial stage, the concentration, which is given on the y-axis of the graph for the reactants A and B, is high, and with the passage of time the concentration decreases. Whereas initially the concentration of products C and D is 0, and with the passage of time it increases and remains and goes to become saturated. At certain point it remains constant. The concentration of reactant is constant and concentration of product C and D is also constant. At this stage, the observable properties of the system become constant at equilibrium and remain unchanged. So this is the equilibrium points of both reactants and products. The equilibrium can be approached from either direction. That is, we can start from the products C and D and reach the reactants A plus D. Hence, the equilibrium can be approached from either direction. The equilibrium can be attained only if the system is closed. Please underline only if the system is closed. The free energy change is 0 at constant pressure, and temperature is also 0. The addition of catalyst helps us in attaining faster equilibrium, but not change the equilibrium state. So catalyst only helps in speeding up of equilibrium, but it does not change the equilibrium state. Few more examples are that of equilibrium of the reaction N2 plus H2 in gaseous state in a forward direction forming the product NH3. In the reverse direction, NH3 splits into form nitrogen and H2. All are in gaseous state. The respective concentrations are shown in the figure. The initial dihydrogen N2 is shown above, and the reactant, another reactant is also shown here, dinitrogen. So this is N2 and this is for H2. They combine to form the reactants ammonia as shown in the figure. Hence the respective concentrations, molar concentrations are shown. In yet another example, that is equilibrium for reaction H2 plus I2 in gaseous state in the forward direction form the product 2HI in gaseous state, and in the reverse direction the product HI splits to form H2 plus I2. So the respective concentrations, please remember concentration. This is the concentration of H2 and I2, and this is the concentration of the product HI. We'll continue our discussions about chemical equilibrium and define a new constant called equilibrium state. A mixture of reactants and products in the equilibrium state is called equilibrium mixture. In this section, we will learn about composition of equilibrium mixtures, relationship between concentration of reactants and products in an equilibrium mixture, and how to determine equilibrium concentration from initial concentrations. We will also discuss about the factors that can be exploited to alter the composition of an equilibrium mixture, which is important for choosing the conditions for synthesis of industrial chemicals such as hydrogen, NH3 and CaO. Consider a reversible reactions AA plus BB in the forward direction forming the product CC plus DD, and in the reverse direction is also possible because it is a reversible reaction. Here capital A and capital B are reactants, capital C and capital D are products. Small a, small b, small c and small d are stoichiometric coefficients of reactants and products respectively. Chemists Cato Maximilian and Peter Wegg proposed in the year 1864, based on their experimental studies, that the concentrations in an equilibrium mixture are related by the equation Kc is equal to C to the power of capital C to the power of small c into concentration of product D to the power of D divided by A to the power of A and concentration of B to the power of B. That is, big bracket shows the concentration. So capital A, capital B, C and D, as well as small a, small b and small c, small d are as defined in the previous paragraph. Here K subscript C is the equilibrium constant and the expression on the right hand side is called the equilibrium constant expression. The equilibrium equation is also known as law of mass action. At a given temperature, the product of concentrations of reaction products raised to the respective stoichiometric coefficient in the balancing chemical equation divided by the product of concentration of reactants raised to the respective stoichiometric coefficient has a constant value Kc. This is known as the law of equilibrium or law of chemical equilibrium. Equilibrium constant for the reverse reaction is inverse of equilibrium constant for reaction in the forward direction. That is, if K dash C is the equilibrium constant for the reverse reaction, then the relationship between Kc and K dash C is Kc is equal to 1 over K dash C. Let us make a general tabulation for relation between equilibrium constants for a general reaction and its multiples. So chemical equation AA plus BB forming Cc plus Dd, which is a reversible reaction. The equilibrium constant is K. In the reverse direction, suppose Cc plus Cd become the reactants and get back the original in the reverse reaction AA and BB, then the equilibrium constant will be designated as K dash C, which is equal to 1 over Kc. Generally, for any other chemical composition, NAA plus NBB combining in the forward direction NCC plus NDD. So please note very carefully the small letters and capital letters in this chemical equation. Here the forward equilibrium constant K double dash C is equal to Kc to the power of n. Now we will take up some forward example. Question number 1. The following concentrations were obtained from the formation of NH3 from N2 and H2 at equilibrium at 500 Kelvin. That is, N2 is equal to, concentration of N2 is equal to 1.5 into 10 to the power of minus 2 moles. And concentration of H2 gas is 3.0 into 10 to the power of minus 2 moles. And NH3 equals 1.2 into 10 to the power of minus 2 m. So we are required to calculate equilibrium constant. Let us solve it. The equilibrium constant for the reaction is given by, for the reaction is N2G, the given equation, plus 3H2G with forward and reversible reaction is 2NH3 in gaseous form can be written as. Please note that on the left hand side both the reactants are in gaseous form, on the right hand side also it is a gaseous form, indicating that it is an equilibrium reaction. So the constant value, as we know, is given by Kc is equal to NH3, that is the product to the power of 2 divided by N2G to the power of 1, because A is 1 here, and H2G to the power of 3. So substituting the given values, 1.2 into 10 to the power of minus 2 whole square divided by 1.5 into 10 to the power of minus 2 into 3.0 into 10 to the power of minus 2 whole cube. Simplifying, we get the answer as 0.106 into 10 to the power of 4. Please simplify this, substitute and simplify the values yourself and get the answer as 0.106 into 10 to the power of 4, or it can be written as 1.006 0.06, that is shifting the decimal place into 10 to the power of 3. Next question. At equilibrium, the concentrations of N2 is given as 3.0 into 10 to the power of minus 3 moles. O2 equals 4.2 into 10 to the power of minus 3 moles, and NO equals 2.8 into 10 to the power of minus 3 moles in a sealed vessel at 800 Kelvin. What will be the Kc for the reaction N2G plus O2G? Reaction combining to form 2NOG. This is a equilibrium equation. For the reaction, equilibrium constant Kc is given as Kc is equal to, that is the product is NO whole square, because 2 is stoichiometric coefficient is 2 whole square divided by N2 to the power of n and O2 to the power of n, because here the coefficients are 1 each, that is small a equals 1, small b is equal to 1, and small c is equal to 2 here, 2 coefficient 2. So putting the given values, substituting, we get the answer as 0.62. Homogeneous equilibria. In homogeneous system, all the reactants and products are in the same phase. Example, N2 in gaseous state plus 3H2 in gaseous phase combine with forward and reverse reaction combine to form 2NH3 gaseous. So, in this equation, reactants and products are in homogeneous phase. Some more examples are CH3COC2H aqueous plus H2O liquid, forward and reverse reaction forming the product CH3COH aqueous plus C2H5OH aqueous. So both left side and right side are in the same phase, that is a solution phase. Another example is Fe3 aqueous plus SCN minus aqueous combined to form FeSCN2 plus aqueous, and this reaction is possible in the reverse direction also. Hence, these are the reactants and products are in homogeneous solution phase. Equilibrium constant in gaseous systems. So far we have expressed equilibrium constant of reactions in terms of molar concentration of reactants and products, and we use the symbol Kc for the same. For reactions involving gases, however, it is more convenient to express the equilibrium constant in terms of partial pressure. Please remember, for gaseous system we use partial pressures. So, recalling PV ideal gas equation, PV is equal to nRT. That can be written as P is equal to N by V RT. Here, P is pressure in Pascal. Please recall that 1 Pascal PA is equal to 1 Newton per meter square, or 1 bar is equal to 10 to the power of 5 PA is the number of moles of the gas. N is the number of moles of the gas, and V is the volume in meter cube, and capital T is the temperature in Kelvin. We can write N by V as a concentration in moles per meter cube. If concentration C is in moles per liter or mole per decimeter cube and P is in bar, then we can write P is equal to NCR. P is equal to C into RT. This C we can also write as P is equal to C is the concentration of the gas into RT. So in this equation, the value of R is 0.0831 bar per liter per mole. At constant pressure, if P is constant, so from this equation we can write P is partial pressure is proportional to the concentration of the gas. So for example, consider an equation H2 in gaseous state combines to form I2 in gaseous state with forward reaction 2HI in gaseous state, as well as the reverse reaction is also possible in this. We can write the value of Kc as Kc is equal to product Hi whole to the power of concentration of Hi whole square divided by H2 concentration of H2 reactants H2 and I2 all are in gaseous state. Or we know that since concentration is proportional to the pressure, that is Hi gaseous into RT can be written as PHI, and I2 is equal to I2 into gaseous state into RT. pH2 is the pressure of H2 is concentration of H2 into RT. R and T are all constant for any reaction, and H2 is the concentration. So we can substitute the values of Hi, H2 and I2 as PHI square of divided by pH2 into PI2. Let this relation between Kc and the pressures be equation 2 for the reaction in chemical biome mentioned in this example. In general, we can write for any gaseous phase reactions AA plus BB forward and reverse reaction to form CC plus DD. Here the left side is reactants and right side is the product. So we can write, when we express in terms of pressures, we can write another use constant Kp is equal to Pc into Cc into Pd to the power of D, Pa divided by reactants Pa to the power of A, Pb to the power of B. Let it be equation 3. This is nothing but we are using the stoichiometric coefficients for reactants and products, and the equation is Kp equals Pc to the power of C, Pd to the power of D, Pa to the power of A into Pb to the power of B. Let it be equation 3 as shown on your screen. So this can be simplified and written as Kp into Kc into RT to the power of delta Ng, where delta Ng is the number of moles of gaseous products Ng minus number of gaseous reactants. Delta Ng is the change in the balanced chemical equation. The table number 3 shows the equilibrium constant Kp for some selected reaction. For example, the first reaction is N2 plus 3H2 both in gaseous state combined to form 2NH3, which is a product. So this reaction is an equilibrium reaction, and both forward and reverse reactions are possible. The value of Kp for this reaction is given as Kp is equal to 6.8 into 10 to the power of 5 at 298 Kelvin. Similarly, the value of Kp is 41 for at temperature 400 Kelvin. When the temperature is 500 Kelvin, the value of Kp is 3.6 into 10 to the power of minus 2. Please note down the different reactions, that is second and third also given with the value of Kp given in column number 3 and temperatures in column number 2. Now we will consider some problems. Question number 3. PCl5, PCl3 and Cl2 are at equilibrium at 500 Kelvin and having concentration 1.59 mole for PCl3, 1.59 mole for Cl2 and 1.41 mole for PCl5. Calculate the value of Kc for the reaction PCl5 reactant forward reaction PCl3 plus Cl2 and reversible. Both forward and reversible reactions are possible. Let us solve it. At equilibrium, apply the formula Kc is equal to concentration of products PCl3 into concentration of Cl2 divided by concentration of reactant PCl5. Substituting the values, we get the answer as 1.79. This is the answer. Next question. The value of Kc is equal to 4.24 at 800 Kelvin for the reaction CO plus H2O both in gaseous state, forming forward reaction CO2 gas plus H2 gas products CO2 and H2 gas. Calculate the equilibrium concentration of CO2, H2, CO and H2O at 800 Kelvin. If only CO and H2O are present initially at concentration of 0.1 mole each. So the products, the concentration, initial concentration is 0.14. Let us answer it. So write down the reaction, given reaction as shown on the screen. And the next step, we will write the initial concentration. So initial concentration of CO is given as 0.1 mole and initial concentration of H2O is 0.1 mole. And we have to assume that CO2, concentration of CO2 initially is 0 and concentration of H2O initially is 0. Then let X mole per liter of each product be formed. So let the concentration be X mole per liter for each of these products, and at equilibrium substituting the values 0.1 minus X mole of CO and 0.1 minus X mole of H2O reactants, and the right hand side let it be at equilibrium X mole respectively for CO2 and for both and H2, where X is the amount of CO2 and H2 at equilibrium. Hence, equilibrium constant can be written as, applying the formula, Kc is equal to x square divided by 0.1 minus x whole square. That is equal to, the value is given as 4.24. Now simplifying the equations and making a quadratic equation, x square is equal to 0.024 plus 4.24 x square minus 0.848 x. This is a quadratic equation of the form given in the insert box as ax square plus bx plus c equal to 0. Applying the solution using the quadratic, our mathematics relation, x solution as x is equal to minus b plus or minus square root of b square minus 4ac over 2a. Here the value of a is 3.24 and b is minus 848 and c equals 0.02424, and substituting the values in the solution equation, we get the values of x1 as 0.067 and the value of x2 is 0.194. We can reject the value of 0.194 as concentration of reactant is more than the initial concentration. Hence, substituting the equation, we can find the x value of x as 0.067. Therefore, concentration of CO2 equals concentration of H2, which is a product, equals to 0.067 x. And substituting the values, for reactants, we get the concentration of CO and concentration of H2O as 0.033. We will take the next question. For equilibrium, 2 NOCl in gaseous state, forward reaction is 2 NO gaseous plus Cl2. So reverse reaction is also possible because it is a equilibrium reaction. So the value of equilibrium constant Kc is given as 3.75 into 10 to the power of minus 6 at 1069 Kelvin. Calculate the value of Kp for the reaction at this temperature. So applying the formula, Kp is equal to Kc into RT to the power of delta n. So we have to calculate the value of delta n from the stoichiometric constants. Therefore, delta n is equal to coefficient of NO2 plus 1 on the products minus coefficient of the value of n number of moles for reactants, that is 2. So the answer is delta n is equal to 1. Substituting in the above equation, we get Kp is equal to 3.75 into 10 to the power of 6 into 0. The value of we have to remember the value of R is 0.0831 and temperature is given as 1069 Kelvin. Simplifying, we get the answer of Kp as 0.033. With this, we come to the conclusion of homogeneous equilibria. Now we will solve some multiple choice questions. Question number 1. A reaction is said to be in equilibrium when 4 choices are given. You have to identify the correct answer. So you're applying and remembering that a reaction is said to be in equilibrium when the rate of transformation of reactants to products is equal to the rate of transformation of products to the reaction. This is the correct answer. So option A is the correct answer. Please mark it. Next question. Which of the following is not true for a reversible reaction? You have to remember your knowledge of equilibrium conditions for reversible reactions. 4 answers are given. The reaction does not proceed to completion. It is not be it cannot be influenced by a catalyst. Number 3 is number of moles of reactants and product is always equal and it can be attained only in a closed container. So here we have to mark the reason which is not true. The answer is which is not true is C. See here the number of moles of reactant products can be different also. So option C is not true. Option C is not true. Next question. The equilibrium between water and its vapor in an open vessel. So 4 options are given. The equilibrium of water and vapor can be achieved in an open vessel. Underline open vessel. So this is not true. Depends on pressure. Cannot be achieved. So depends on upon temperature. The reason is the equilibrium between water and vapor cannot be achieved in an open vessel. So option C is the correct choice. So in an open vessel, water vapor and equilibrium cannot be achieved. So option C is correct. Next question. Which of the following is an example of homogeneous equilibrium? 4 reactions are given and different states. Remember that for both products and reactants, the phase should be same. So if you observe, A has got different phases, solid and gaseous. B has got all the 3 gaseous. So option B is the correct answer. You please mark it. Next question. Consider the following graph and mark the correct statement. Please see and recall this we have explained already in this section and see the graph. So, and mark the correct statement. Chemical equilibrium in H2G plus I2G forward reaction HIG can be attained from either direction. This is the correct statement. So, A is the correct statement and mark it. Next question. Match the column 1 with column 2 and mark the appropriate choice. Four options are given in this question. Column 1, capital A is liquid to vapor, solid to liquid, solid to vapor, and solute S to solute solution. So choice in column 2 are saturated solution, boiling point, sublimation point, and melting point. So liquid to vapor is formed with the boiling point. So capital A should match with 2. So here the 2 is only option C. So for again we can see solid to liquid is melting point. So it should be 4. That is solid B should be 4. Where is that? C. So option C is the correct answer. Mark it. Now we'll take up NCERT exemplars. Question number 7. What is observed at equilibrium point in the given reaction PCl5 reversible reaction PCl3 plus Cl2? So what is observed in this we have to know. Here equal volumes or equal masses, the concentration is constant, our reaction comes to stop. We know that for equilibrium point, the concentration becomes constant at equilibrium. Therefore, mark it. That is option C is the correct answer. Next question is, we know that the relationship between Kc and Kp is Kp equals Kc into RT to the power of delta Ng. What is the value of delta Ng for the given reaction? So here we have to calculate the stoichiometric equations. We have to calculate as shown. Delta Ng is equal to number of gaseous products minus number of molecules in moles in gaseous reactants. So here we should know that for the products NH3 plus HCl it is 1 plus 1 because stoichiometric coefficient is 1 plus 1. On the left hand side there is no gaseous reactant. Hence, the N of gaseous reactant is 0. Therefore, the value is 2. The correct answer is given as option D. Please mark it. Next question is, for the reaction H2 gas plus I2 gas, reversible reactions, 2HI gas, the standard free energy delta G naught is greater than 0. The equilibrium constant would be, we are required to calculate the value of constant from the given. A is k is equal to 0, k is greater than 1, k is equal to 1 and k is less than 1. So you please apply the logic. So we know the formula delta G, standard value of delta G is given by the formula delta G naught equals minus RT into natural log K. So in this equation, if natural log K is negative, then delta G is positive. That means log is negative means K greater than 0. That is so, but in this, because K greater than 0, that means it is less than 1. So option is D. Mark it. Next, which of the following is not a general characteristics of equilibria involving physical processes? Four options are given. You study them all the four, pause the video and answer. The option C is not possible because all the processes stop at equilibrium is not possible. All others are the general characteristics of the equilibria. So option C is not a general characteristics of the equilibria. Next question. For the reaction 2SO2G plus O2G, 2SO3G, what is the value of Kc when equilibrium concentration of SO2 is 0.60 moles, concentration of O2 is 0.80 moles, and concentration of SO3 is 1.90 moles. So we have to calculate it. Make the calculations as given, and the answer is, substituting the given values, we get the answer as 12.229 liters per mole. So this is given in option A, and please mark it. The next question. For the following reaction, NO plus O3 reversible reaction forms NO2 gas plus O2 gas. Both are all left hand side and right hand side are gaseous. The value of Kc is given as 8.2 into 10 to the power of 4. What will be the value of Kc for the reverse reaction? So we know that for reverse reaction is the reciprocal of the Kc. Therefore, it will be the option is given in the value of Kc for the reverse reaction is reciprocal of 1 over 8.2 into 10 to the power of given in option B. Please mark it. With this, we come to the end of lecture 1 of unit 6 on chemistry on equilibrium. In next session, we will take up heterogeneous equilibria and other chapters. Till then, goodbye.